Stop relying on simple expiration. A stolen refresh token grants indefinite access, bypassing standard security measures. The core defense is separating the short-lived access token, typically 5 to 15 minutes, from the long-lived refresh token. The access token is stateless, validated via its signature, usually JSON Web Token format. The refresh token, however, must be stateful and stored securely server-side, mapped to a specific user session identifier. Never store sensitive user data within the refresh token payload itself. The client uses the refresh token only to request a new access token from the authorization server's dedicated token endpoint, typically using the grant type refresh token. This separation minimizes the window of opportunity for resource server compromise if an access token is intercepted. Client-side storage dictates security posture. For web applications, the most robust method is using HttpOnly Secure cookies. This prevents client-side JavaScript access, mitigating cross-site scripting or XSS theft vectors. Set this same site attribute strictly to lax or strict to prevent cross-site request forgery. Avoid storing refresh tokens in local storage or session storage. These are highly vulnerable to XSS attacks because JavaScript can easily read them. For native mobile applications, utilize platform-specific secure storage mechanisms, such as the Android Key Store system or iOS keychain services. These systems encrypt the token using hardware-backed keys, ensuring the token never resides in plain text memory accessible by other applications. Simple expiration is insufficient because a compromised token remains valid until its expiry date, potentially days or weeks later. Refresh token rotation, or RTR, mandates that every time a client uses a refresh token to obtain a new access token, the authorization server issues a completely new refresh token. The old token must be immediately invalidated. This single-use policy is the foundation of proactive defense. If an attacker intercepts the token exchange request, they gain only a single-use token that becomes useless the moment the legitimate client performs the next rotation. This dramatically limits the utility of a stolen credential. Server-side implementation requires tracking token lineage. When the client presents refresh token A, the server verifies its validity and issues refresh token B. Crucially, the server must immediately mark token A as used and invalid within the session database. If token A is presented again, this indicates a potential replay attack or token theft. The server must not only reject the request, but also immediately revoke the entire token family associated with that session, including token B and any subsequent tokens derived from it. Use a database transaction to ensure the invalidation and issuance steps are atomic, preventing race conditions during concurrent requests. Detecting token reuse is critical for session integrity. Implement a grace period, typically 30 seconds, where the server accepts both the old and new refresh tokens. This handles network latency issues where the client might receive the new token slightly delayed. However, if the old token is presented outside this grace window, or if the new token is presented before the old one is invalidated, trigger the full session revocation. The revocation process must delete all associated session records and notify the user via email or push notification about the security event. This immediate, aggressive response minimizes attacker dwell time and prevents further unauthorized access.
Token binding ensures the token can only be used by the specific client that requested it. The most robust method is using Mutual Transport Layer Security, or MTLS, where the client presents a certificate during the token exchange. A simpler, modern approach is demonstrating proof of possession, or DPoP. DPoP requires the client to generate a unique public-private key pair and sign the token request with the private key. The resulting access token contains a confirmation claim, or CNF, linking it to the client's public key. The resource server verifies this signature before granting access, preventing token use by an unauthorized third party, even if the token is stolen. Access tokens must be short-lived, ideally 5 to 15 minutes. This limits the damage if the token is leaked, as the attacker's window of opportunity closes quickly. The client application must be engineered to handle the 401 unauthorized response gracefully. Upon receiving a 401, the client should automatically attempt the token refresh flow using the stored refresh token. If the refresh fails, only then should the user be redirected to the full logged-in process. Avoid unnecessary network traffic by proactively checking the access token expiration time locally before making an API call, initiating the refresh slightly before expiry to maintain a seamless user experience. Effective revocation requires server-side state management, even for JSON Web Tokens. Use the JSON Web Token Identifier, or JTI, claim to uniquely identify each token instance. Maintain a centralized revocation list or database mapping active JTI values to user sessions. When a user logs out, or when a security event triggers revocation, immediately add the current refresh token's JTI and all associated access token JTIs to this list. Resource servers must check incoming access token JTIs against this list before processing the request. This ensures immediate termination of access, overriding the token's inherent expiration time and preventing unauthorized use. Implement robust logging on the authorization server, specifically tracking all token issuance, refresh, and revocation events, including source IP addresses and user agent strings. Monitor for anomalous behavior, such as rapid token rotation attempts from different geographical locations or excessive refresh failures. If a potential leak is detected, immediately force a global session logout for the affected user, invalidating all active refresh tokens. Provide users with a mechanism to view and revoke their active sessions, similar to device management interfaces, empowering them to manage their own security posture and respond quickly to suspicious activity. The secure flow mandates client requests token pair, server issues access token A and refresh token R1. Client stores R1 securely. When A expires, client sends R1 to the token endpoint. Server validates R1, checks for reuse, issues access token B and refresh token R2, and immediately invalidates R1. If R1 is reused, the server invalidates R2 and all subsequent tokens, forcing reauthentication. This continuous rotation and immediate invalidation, combined with HTTP-only storage and DPoP binding, forms a resilient defense against credential theft and replay attacks, ensuring session integrity across all client types.